Hello everyone, in this short video I will go through the basics of machine learning pipeline, or the basic steps that you follow in order to train a model and to evaluate the performance, how we can check the accuracy of the system. So in this topic, we are going to talk about basics of machine learning pipeline, what is data collection, pre-processing, all the different steps which are involved in this process. So like we saw previously, machine learning is once again the field of AI that gives the computers ability to learn from the data without explicit programming. And the machine learning pipeline, it consists of a series of steps which are used to basically train and test our data. So it involved various stages. We have the data collection, we do some pre-processing, we do feature extraction, and then we do the data distribution, then we apply the machine learning algorithm. After that, we do the evaluation and then deploy our model. Now, to do all these different steps in the machine learning, there is a specific library available in Python which is called the scikit library, and the keyword used in Python is called sklearn. So this sklearn is a presentation of the scikit library, and it contains different modules which can be used for pre-processing the data, that can be used for extracting features, for distributing the data into different sections, and even running different machine learning algorithms. We can use this library. So first of all, the first step we have is called the data collection. So in data collection, what we do is basically we first of all find useful data. It can be in the form of text, it can be tabular, it can be images also. We can have a folder that contains thousands of images. So that data we need to load into our Python program, the one which we will use to train our model. So the data loading step, we talked about this before also. We can use the pandas library to load our data into the program. And besides the pandas library, there is also in the sklearn, there are different data sets available. So any of you, if you are doing the iris data set, iris project, where you have to classify the iris flower into different species, so you can directly load the iris dataset without actually download any specific file or loading a CSV file. But in our case, in this example, what we are going to do is we are going to load our dataset, which is available in this ortho_dataset file. So what I'm going to do is, here I have the ortho dataset. I can load it here into my current folder. Let me refresh it. Yeah, so let me load the data set here into our folder. So what I'm going to do here is I'm going to use the pandas library. So I will say import pandas as pd, and our data is equal to pd.read_csv. This is the same function we used last time to load a specific file into our program. So this time I will use the file ortho_dataset.csv. So once the file is loaded, I can look at the head of the data. So by running this command, I will be able to see that this dataset contains various features which can help us identify if a patient is affected by different orthopedic diseases like spondylolisthesis, or so if the patient is affected by spondylolisthesis or disc hernia. Now, once the data is loaded, we saw the head of the data, so it contains different parameters, and you can notice how many data points we have. So instead of going through like this, we can just type a simple command that says data.shape. So when I enter this data.shape, it shows me that there are 310 input data points, and there are total 7 columns. So out of the 7 columns, you will notice that the 6 of the columns contain features of the data. that are different properties of the patients, and the last column here, which is the class column, that is our output labels. Remember, when we do classification, we have our data which contains the label. So here the data set is in this file along with the features as well as the class labels. We will see later on how we can separate them as well. So back to the presentation. So this is how you can load the data into our program, and once again, it's very important to have a good quality data. The better the data we have, the better the algorithm will be trained, and the evaluation or the model will be able to provide better accuracy and results. The next step we have after we load the data is to pre-process. Sometimes what we can do is we need to convert our data into a specific range. For example, that is called data normalization. So in this data set, we don't need to worry about that much for the data normalization. But here notice the values are in the 60s to 20, 50, 40, 100. So they are in between from 0 to 100 range. But imagine we have let's say some values which are in million, let's say the sales of some data of some company, and then we have the age of the employees which is between 0 to 100. And if we have imbalance in the values of the data, we can normalize the data using the pre-processing techniques. Sometimes we also need to transform the categorical features or categorical class values as well. So for example, here our output class is text. It is written in the form of text here, which is abnormal or normal. So later on we will see how we can convert this class labels into 0 or 1. So for example, abnormal will be represented by 0, or normal patients can be represented by 1. So we will see later on how we can do that using a pre-processing technique which is called the label encoder. Label encoder, what it will do is it will receive a data column, for example data class, and what it will do is it will transform. So it has a function fit underscore transform. What that will do is it will basically transform the data from text into coded column. So abnormal labels will be represented by 0 and the normal labels will be represented by 1. So what we can do is, let me just before we can do the label encoding, let me just show you how we can represent this data. So here, if I want to further analyze the data here, what I can do is I can do the analysis for the classes. So here, if I extract this, let's say if I want to plot PLT for plot, I have to import it first. So from matplotlib, if I do import pyplot as PLT. So once I import the plotting tool, plotting modules, what I can do is I can try to plot this. I will say PLT dot plot, and I want to, or in fact instead of plot, let's do the histogram plot. So what the histogram plot will do is I'm going to access the data that I have loaded, but only the specific column, that is the class column. So if I load this data and do a histogram plot, so you can see here these are the number of patients which have abnormal class label, and these are the number of patients which have normal class label. So what I can do now is I can use the label encoder on this data. So here once again the label encoder, we can use it with the sklearn pre-processing import. So what I will do is I will say from sklearn dot pre-processing modules, I'm going to import label encoder. So once I import the label encoder, what I'm going to do now is that with the help of this label encoder, I will load it into a variable. I will say encoder is equal to label, let me write it correctly, encoder. So once we have loaded this, what we can do is we can transform the data. So the data we have in our class column right now, what I can do is, using this encoder, I can use its function, which is fit underscore transform. So here, using the encoder's fit underscore transform function, I can provide the same column which I want to transform, that is my class labels. So here, if I run this one and after that I print, let's say, let me just show you here. So before doing any label encoding, what I'm going to do is I'm going to print the data with the class labels, and I'm going to print its head. And the same thing I'm going to do is, after encoding, I'm going to print the data with the class label comment. I'm going to print the head again. So head will print the first initial 4-5 values and the last 4-5 values. So this print, before doing any label encoding, it will show me that my data labels are in the form of text, that is abnormal or normal. But after encoding, these labels will be converted into integers, to number format. So here you will see, before we have the labels in the form of abnormal and normal, but after encoding, notice our labels, they are converted into 0 and 1 format. So this is how we can use label encoding on our data. So here, let me correct this also. So the next step we have is called feature extraction. Now this step is a little complex, where we extract useful information from our input data. In the projects that we are going to do, the features, they are already provided in the data set. So these are the features, the important features which I have already extracted and are available in the data set. But in complex classification algorithms, in complex projects, what we do is, our features are not available like this. Imagine I have a picture which is, let's say, the size of the picture is 800 by 800. So it has thousands of pixels inside the image. So which of these are important? We need to extract the important features or important pixels in images. So that will be complex, where the features can be thousands of features. There we will use different transformation techniques, like the wavelet transform or Fourier transform or morphological processes. So feature extraction, in this course we are going to skip this one. We are going to assume that the data that is provided to us already has the features available. So once the features are extracted, the next step is to do the data distribution. So remember, in machine learning algorithms, in classification, we have the training steps. In training step, whatever we have, let's say we have input features, which can be a collection of columns, that can be 1, 2, 3, 4, 5 features we have, and then we have our output labels. So our output label can be, let's say, true or false, or it can be 0 or 1, something like that. So based on the input features, our output labels are provided. So here in this case, in this data set, you can see these are all our inputs. These are our inputs, which are our features. And then this side here, this is our output class label. In data distribution, what we are going to do is, we are first going to split our inputs and outputs. So these are our inputs, which is X, and these class labels, that is our output. So once we have our inputs, which are all these input features, this is our inputs X, and this, our output labels, will be Y. So once we have our input and output separated, what we are going to do is, we are going to do data distribution. So in data distribution, our inputs and outputs, we are going to split. For example, here in this data set, we have total data of 310 students, or of 310 patients. So what I'm going to do is, I'm going to distribute this data. I'm going to split this data into what we call training and testing. So normally we use 70% of the data for training and 30% of the data usually is used for testing. So the inputs which we are using for training, we call them, it's a standard, we use the X which are used for training. The output labels which I am using for training, we call them Y underscore train. And similarly for testing, later on once the system is trained, we use X underscore test variable to store the test inputs. And similarly Y underscore test, we are going to use them to test our prediction. We are going to test the performance of the system based on those testing data sets. So what we are going to do is, from this data set, first we are going to split it into the inputs and the outputs, which will be X and Y. Once we have X and Y, we are going to split it further into the train, X train, Y train, and X test and Y test values. So to do that, first we need to find X and Y. So the X, which are our input features, are basically all the initial columns except this class column, which is our output labels. To get X, it's very simple. We can use the command. Let me do it here. So I can use the command here, X, which will be equal to our data, but I'm going to use the command which is data.drop. So here, let me write it down here, which is data.drop. Let me see the exact, yeah. So here it will be data.drop, and inside the drop function I need to provide the column which I don't want to include in the X values, and that is basically the name of the column is the class column. And when I provide access is equal to 1, that means only select the whole column, not the row. So that will basically extract the X values out from that column. So now if I do X dot head, it will show me the feature columns only. Pelvic incident, there is pelvic tilt, there is lordosis angle, and so on. There is pelvic radius and spondylolisthesis degree. So I extracted the inputs. Similarly, I can get the Y values also. So Y will be simply the last in the data frame. It is just the last column that contains the class labels. So here, after that, if I do Y dot head, so it's going to show me the initial and the final value. And notice here, the class values are already encoded now. Abnormal values are 0, normal values are represented by 1. So once we have split the inputs and outputs, now we are going to do what is called the data distribution. We are going to split the data into training and testing. So to do that, we have the sklearn model selection module. So here what I'm going to do is I'm going to import, so let me do this here. So I'm going to import the train test split module from the sklearn library. So what I'm going to do is I'm going to split the X and Y that we have, X and Y. I'm going to split it into X underscore train data, comma, X underscore test data. Then I'm going to get Y underscore train data and Y underscore test data. And how I'm going to do that? I'm going to get it using the module which is this one, train test split. So if I put it here, train test split, it needs some input. What inputs it need? It needs the X and Y inputs. So I will say the inputs are X, comma, Y. These are our inputs and Y are our labels. And then I'm going to provide the split. How I want to split? I will say test underscore size. So here I'm going to provide the percentage in a numeric form. So if I want 30% of my data to be for testing, I will say my test size will be 0.3, that is 30%. And then very important part is the random underscore state parameter. The random underscore state makes sure, for example, if I select 5, so the random underscore state parameter makes sure that from the data set we randomly select 70% for training and 30% for testing. And when I provide a value here 5, that means every time I run my program it will select the same random values so that I can check my training process, I can check my algorithm more properly. If I don't write random state here, what will happen? Every time it will select different data points for training and different data points for testing. So I cannot have a reliable check of my algorithm if every time my data is changing. So if I want to fix it, I need to provide a fixed number. It can be any number here, 10, 15, 20, but every time whatever number you provide, it will generate same number of random data that we select from the input and the output labels. So once I do that, what will happen? It will select 30% data for X train and Y train, and remaining 70% for X train and Y train, and 30% for X test and Y test. Once we have done that, after this what we can do is we can check the shape. I can say X underscore train dot shape, and if I run this you will see it's 217 by 6. So initially our total data had 310 data points, but now it has 217, that is 70% is in the training. And similarly if I do y underscore x underscore test dot shape, so I just want to see how many data points went to the testing phase. So here you will see there are 93. So this is how you can split the data. So once the data is split with the help of data distribution, we have split the data. After that we can do the machine learning model selection. So there are different models available, different machine learning algorithms which are available that will learn patterns from the features that we provide of the data, and they train the model. So one algorithm from them is the support vector machines. So it's a very commonly used method and very popular. It is very useful in predicting and finding the boundary that can easily separate different data points. So based on the features, for example, based on, let's say, for the normal patients, their the pelvic boundary feature, for the normal patient, let's say if it is distributed here. For abnormal patients, it is distributed here. So the goal of the support vector machine algorithm will be to find a boundary that can separate the data points easily. So there are different possibilities. I can put a line boundary here, a vertical boundary. I can put a horizontal boundary like this. I can put a boundary like this. So which boundary is the optimal boundary? That is the goal of support vector machines. So here we can import this model using from sklearn import svm. So this model, once again, what it will do is it will find a maximum margin separator. What does that mean? That means from these data points it will find the data point which is at the most extreme near to the outest boundary, and similarly from the other group it will find a data point which is at the extreme boundary. So it found these two boundaries. Based on that it will generate the support vectors. We call those vectors support vectors, and the goal is to maximize the difference between these extreme data points between two features. And this is only for one particular feature. They will try to do this for all the possible features we have. In this data set we have 6 features. So they will plot this one and this one and this one and this one between normal and abnormal and try to find a boundary that can overall maximize the difference between the two classes, which is normal and abnormal. So this is how support vector machine will work. Now in the projects there are different algorithms like knife Bayes, there is KNN, there is logistic regression. So one important part in the project is that you should explain the machine learning algorithm. You should explain the basics. I will not go into the mathematical details, and you should also not go into the mathematical detail. You just need to provide the basic idea how the algorithm is working. Okay, so to use this one, what we are going to do is I'm going to first import from sklearn. I'm going to import the SVM algorithm, support vector machine. And what I'm going to do is I'm going to load it into my model variable. So I will say model will be equal to svm.svc. svc is for support vector for classification. And the input is I can select a kernel which is equal to linear. So linear kernel means that my algorithm will try to find a linear boundary between our input data. So for some data points, the linear boundary will give me better performance. For some inputs, the linear boundary cannot give me good performance. For image processing, sometimes we have to use different type of kernels. So here I imported the model. So here I loaded the model. The next step we are going to do is, in the next step, we are going to train the model. And training the model, it's not that difficult, it's very simple. I will simply say model.fit. That's the simplest command. I will say model.fit. I will provide the input. So where are the training inputs? They are in x underscore train. Where are my training labels? They are in y underscore train. So using the training data for input features and their labels, I will train my system. So once the training is complete, after the training, what I can do is I can do the predictions. So here, once the training is complete, I will do what is called the predictions. So here, let me do the predictions here. So my predictions, I can load it into this variable predictions. So my predictions will be what? It will be simply model.predict. Let me correct the spelling. So model.predict. Predict means to guess what will be the output labels for the new inputs, the unseen data. And this unseen data we put in the x underscore test variable. So I want the model to find what is its prediction against the test data. I already know what should be the output for the test data. That is already available in the y underscore test. But the predictions will give me its own result. So here, if I do this, let me see. Predictions dot head. So if I try to, sorry, it's not, I cannot do that on this one. So here what I'm going to do is, after that, I'm going to check the performance. To check the performance, what I'm going to do is, I'm going to calculate the accuracy. So to calculate the accuracy, there are different performance metrics which are available in sklearn.metrics module. So in sklearn.metrics module, I can import. So here, after doing the predictions, I can now import from the sklearn metrics. I can import the accuracy score performance. So based on that, I can measure my accuracy. So my accuracy will be what? That will be using this function. Using this function, I will provide the input. The accuracy will be based on the y underscore test values, which is the true output, the actual output, and the predictions that I received from our test. So those predictions will be compared with, let me check the name. So those predictions will be compared here. Spellings are wrong. So these predictions will be compared with the test outputs, and based on that, the accuracy value will be calculated. And here I will check print the accuracy of the model is this one. So here, if I check this, let's see. Here the prediction is not defined, so let me check. I did not run this one. Yeah, so if I run this one now, it will say the accuracy of the model is 0.8709, which is 87.096%. That's a good prediction we are getting, a good accuracy score that we are getting. So once we evaluated the model, after that we can deploy it, we can build a program on top of it, and then we can make a front end interface that can be able to predict any type of input data. So once again, the model that we used, it was for orthopedic patients, and based on their biomechanical feature, the data classified the inputs into normal and abnormal classes. We had 6 features, and we are doing binary classification. Binary classification means when our output has only 2 possible values, abnormal or normal. In multi-class classification, we have more than 2. So here once again, to summarize, we first imported all the libraries that we need, the pyplot, the PLT, we did the model selection for training, test and split data, we do the SVM machine learning algorithm, we similarly get the metrics that we need, the pre-processing modules that we need, we import all the libraries, and then we check our data. We read the CSV file, we check the head of the data. Let me just load it now. So what you have to do is load this file which I have provided. Let me just open this one here. So what you're going to do is you are going to open the notebook using upload and browse. In the week 12 folder there should be a file. Let me put it here, this one again. So this file is the one that you will load from the week 12 folder. So here what we are going to do is, first we have loaded the libraries, and after that make sure the ortho data set is available here, and then we are going to load the data set. Once we load the data set, we can check the head, we can describe it, what's the histogram of the data, and also we can calculate the value counts, the number of classes, the count of each classes. So here if I scroll down and run this one, so you will see this is the distribution. So this is an unbalanced data. You can notice abnormal classes, there are 210 patients with abnormal class and only 100 with the normal class. So in pre-processing we can do more, furthermore we can balance the data, we can do many other stuff. For example, data augmentation, which is used to generate synthetic data, that is not actual data but it is something like that. Similarly, we can use that. Now in the pre-processing we are just going to do the label encoder. You can just run this one and it will see that it will convert the abnormal and normal labels, it will convert them into 0-1 based labels. Once you have done that, after that we are going to do the data distribution. First we are going to separate the inputs and output classes. So using the drop function we can do the same thing. We can extract our class column, we remove that and assign all the remaining columns as our input features, and only the class column that will be my output label column. So once we have the x and y's, we can now split them using the x train, y train, and x test and y test. So here after separating them, now I can do the split using the train test split module with x and y as our inputs. The distribution split is 30%, so that's why I put 0.3, and the random state I'm choosing 4. After that, if I print the train and the test shape, it will show me this values. So there are 217 patients which are now for used, their data will be used for training, and 93 patients data will be used for testing. So then we load the model just like before, svm.svc with the kernel that is linear. We train the model using the fit command, and then we test the model using predictions. So we say svm classifier.predict on the test input data. So once the predictions are complete, we can calculate the accuracy score, which will give me 87% accuracy. And you see it's giving me the same exact accuracy because I'm using the random state here the same number. If I change the number, I will get a different result. So this is how you can work on it. And the last thing I want you to do is to do this exercise. So here, after importing and running each steps, I want you to modify this. I want you to change the train test split from 70 to 30% to 80-20, and change the SVM kernel from linear to polynomial, and then retrain the model and observe the change in accuracy. So I leave this task as an assignment, so I hope you are able to complete this and then submit the modified file on the Blackboard. Thank you everyone.